One way to correct for dependence in our errors is to add lagged dependent variables to the equation, as we will now see in case 2. Let's first have a closer look at the intuition behind this approach. Remember, we have a location model where the errors follow an AR1 process. But if we would now apply this lag polynomial here to both the left and the right-hand side, what would we get? Well, we have the response yt minus its lagged value, which I immediately bring here to the right-hand side. For the constant, we would just be getting the constant again as its lagged value. And if we subtract rho times the lagged value of the error term ut, we would just be getting the IID error epsilon t, since this is nothing more than a rearranged version of the model equation over here. Now, what is the crucial thing about this new model? Well, we have created a model where the error term is IID, namely the epsilon t guy. And how have we done that? Well, we did that by adding a lagged value of our response. Note that the parameter here for the constant term is transformed. But what is actually important is that we have now errors that are IID. Why is this important? Well, we've seen in the first case today that our usual asymptotics go through for IID errors. So this is actually a very nice way to deal with serial correlation in the errors. More generally, this trick also works when we would have an error term that follows an ARP process. Then we would just simply need to add P lagged values to our regression model. Of course, in practice, you might not know what the order of the AR process is. So you could resort to, for instance, information criteria such as BIC to determine how many lags you should add to your model. Now, this was one way to deal with serial correlation in the errors. Another way is to estimate the so-called long-run variance. And let's have a closer look at this route now. In essence, we've seen that the problems arise since the numerator, this guy over here, converges in distribution to this normal with asymptotic variance indicated in red, which is a so-called long-run variance. Now, our problem arose since the denominator of the test statistic, the sample variance of the residuals, converged in probability to the expected value of ut squared, which gave us the so-called short-run variance indicated in blue. And since both did not coincide, the expression did not simplify to a standard normal distribution. Intuitively, the only thing that matters for the central limit theorem is the asymptotic variance of this guy over here. So what can we do? Well, we can evaluate this expression for a weakly stationary process. And that's what we're going to look into in this slide. Now I can first take the square root of t here outside of the variance, and then I need to square it. And then I have a variance of a sum, which is nothing more than the sum of the variances, but I need to take all of the covariances into account as well. Now, how many of these covariances do I have? Well, first of all, I have t of the variances denoted by gamma naught. How many autocovariances do I have? Well, I have t minus 1 autocovariances of order 1 and an additional factor 2, since I have both the autocovariance at lag 1 and minus 1, which are equal to each other. and so on. Now I can further simplify this expression by writing out the sum over the J autocovariances. And what happens now if I let my sample size go to infinity? Well, then I get this infinite sum over here. And of course, the autocovariance of order 1 is the same as the one at -1. So alternatively, I also have this expression. In your assignment, you will have a closer look at the long-run variance for an AR1 model. But what we do know now is that this scaled average goes to a normal distribution with asymptotic variance given by this long-run variance, which we can compactly denote by lambda squared. Now, suppose that we can consistently estimate this long-run variance. How can we then make use of this estimator to account for serial correlation in the error terms and fix the asymptotic distribution of the test statistic? Well, let us here pre-multiply this test statistic by this ratio of the short-run variance estimator and the long-run variance estimator. Then after plugging in the expression for the test statistic, the terms with the sigma hats cancel out, and I'm only left with the rescaled version of this guy over here. I know that the numerator goes to a normal distribution with variance lambda squared, as written at the top of the slide. And then this denominator goes, of course, to lambda squared. So the continuous mapping theorem tells us that the asymptotic variance of this guy is given by the asymptotic variance of the numerator pre and post multiplied by the probability limit of our denominator. And as we can see, this just simplifies again to a standard normal distribution. And that's good because we have again valid inference if when the error terms are serially correlated, if we take the long-run variance into account. Now, how can we estimate this long-run variance in practice? Well, based on the expression that we derived, we could consider this estimator over here, where we actually use sample analogs as plugged into all expressions. But unfortunately, this one will not converge in probability as there is too much randomness involved. Note that for a sample of size 100, we would have 99 observations available to compute the autocovariance of order 1. Since the first observation doesn't have a previous value, we would have 98 observations to compute an autocovariance of order 2 and so on. And so for the autocovariance of order 99, we would only have one observation available. So it's much more difficult to estimate the higher order autocovariances. And moreover, we also expect that they are far less important. So when we let the sample size go to infinity, well then, yes, many of them are estimated more accurately as we would expect. But we would need to estimate many more of them. And the estimates get very noisy for higher order lags. Why? Well, since we don't have many observations available to estimate them. That is why you should only gradually introduce more autocovariances. And the so-called Newey West estimator, for instance, does that. It cuts off the autocovariances at a certain lag Q. Note that there exist other long-run variance estimators as well, but this Newey West one is a very popular one. Now, this brings me again to the end of the video where we discussed dependent processes, law of large numbers, central limit theorem for dependent processes. And we also have seen how to derive the limiting distribution of the test statistic in a very easy model when the errors are both IID and serially correlated. With these lecture slides, you should be able to prepare your third tutorial assignment. Good luck.